Welcome to this explainer. Today, we're diving deep into Cambridge Syllabus 0606, and we're tackling a massive topic, mastering circular measure and the absolute power of radians. But listen, we aren't just going to look at the math today. We're going to look at the strategy behind the math. I want you to start thinking of yourself as a photographer. What does a master photographer do? They don't just point and shoot blindly. They find the perfect angle. They frame their subject flawlessly. And in a mathematics exam, you have to do the exact same thing. Find the perfect angle, literally and mathematically, and frame your answer to highlight the key evidence the examiner is desperately looking for. Let me tell you about two types of students I see all the time. Let's call them Alex and Sam. When faced with a complex circular measure question, Alex goes into overdrive. Alex overloads the exam paper with every raw mathematical fact they can remember about circles, dumping formulas everywhere with absolutely zero structure or analysis. The examiner looks at it and just sees a wall of chaotic numbers. Then you have Sam. Sam is the complete opposite. Sam is constantly watching the clock, rushing through the paper, and entirely missing the specific command word requirements. Sam calculates an area when the question asks to show that the angle is a certain value. Both Alex and Sam end up with exam papers covered in red pen marks, bleeding points on questions they actually knew how to solve. Today, we transition away from the chaotic approaches of Alex and Sam. We're going to upgrade your foundational knowledge from basic degrees to a much more elegant, mathematically sound system called radians. And I'm going to show you exactly how to frame your answers for maximum marks. To really ground this mathematics in reality and understand why framing the problem correctly is so absolutely crucial, consider the Singapore Flyer. It's a massive observation wheel with a 75-meter radius, and it takes exactly 30 minutes to complete one full constant speed rotation. Now imagine you're an engineer working on this. When engineers calculate how fast those individual passenger capsules are traveling through the air, they aren't just taking wild guesses. They are solving a massive, high-stakes, real-world circular measure problem. Think about how Alex would handle this engineering problem. Alex would probably calculate the area of the entire wheel, the circumference, the volume of the capsules, and write a disorganized report that completely misses the point. Sam would rush it, maybe divide 75 by 30 and get a completely meaningless number because Sam didn't decode the core requirement. But a top-tier Cambridge student? They know they need to find the exact arc length the capsule travels over a specific time interval. And to do that efficiently, without messy fractions, they rely on the exact mathematical principles and sleek formulas we are unpacking today. They frame the problem. They extract the required data. They execute. So here is our perfectly structured game plan for today to get you fully exam ready and scoring in the top percentile. First, we are going to debunk the 360-degree myth. Second, we'll formally define radian measures so you understand the why behind the numbers. Third, we'll look at the formula advantage. This is where we literally see red pen marks turn into green check marks. And finally, Section 4, Cambridge Exam Mastery, where we'll put you on the clock in an interactive workshop to dissect real past paper questions. Let's dive in. Let's move straight into our first section. We need to uncover why we even use 360 degrees in the first place, because this is where so many students get completely tripped up. I absolutely love this quote from Maynard James Keenan. "A circle is the reflection of eternity. It has no beginning and no end." It brilliantly illustrates the conceptual beauty of a circle. It's smooth, it's continuous, it's perfect. But mathematically, to calculate an area or a perimeter on an exam, we can't just write down, "it's eternal." We have to measure it. And historically, to do that, humanity decided to slice this perfect shape up into completely arbitrary little pieces called degrees. When students like Sam try to rush through questions involving circles, they just blindly punch 360 into their calculators because it's what they've been taught since primary school. But in advanced mathematics, blindly relying on degrees is like trying to measure the volume of an ocean using a teaspoon. It's clunky, it leads to massive rounding errors, and quite frankly, there is absolutely no inherent foundational mathematical law that dictates a circle must be divided into 360 parts. None whatsoever. So where did 360 come from? This is the crucial point. Our traditional 360-degree system is literally just an ancient, inaccurate calendar assumption. It's widely thought to have originated with Sumerian shepherd astronomers thousands of years ago. Back then, much of early mathematics was tied directly to looking up at the night sky. These early astronomers mistakenly believed there were exactly 360 days in a year. Because of that slight miscalculation, they divided the great circle of the heavens into 360 parts, one for each day.
And crazy enough, we have just been blindly using this astronomical quirk for millennia. But as we advance into higher-level mathematics like Cambridge Syllabus 0606, dragging this arbitrary number into our equations actually overcomplicates our formulas. It creates messy fractions that eat up your precious exam time. It's time to let go of the Sumerian calendar and move to a much more natural, structural measurement. And hey, before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's step into the real core of today's strategy. This brings us to Section 2, and a mathematically superior way to frame and measure angles, the radian. Forget the ancient calendars, we are going to use the pure geometry of the circle itself. We need to define this perfectly, so grab a pen and visualize this with me. This is your foundation. Imagine drawing a circle. Now take the exact length of that circle's straight radius. Imagine you could pick that radius up, bend it, and wrap it perfectly along the outside curved edge, the arc of the circle. The angle that is created back at the center of the circle by that specific wrapped arc length is exactly 1 radian. Do you see how elegant that is? It's a unit of measurement born directly from the circle's own internal proportions. It's not a made-up human number. It's the language the circle speaks natively. When we talk about structuring your exam answers, knowing this definition means you aren't just memorizing. You are understanding the framework. You're building a logical point, evidence, and explanation. Now, to put that pure geometric concept into a perspective our brains are already used to dealing with, 1 radian is approximately 57.3 degrees. But please don't write 57.3 on your exam paper unless explicitly asked to convert. I'm just showing you this to give you a mental anchor. Here's why this concept is an absolute game changer for your exam potential. You already know that the total circumference of a whole circle is 2 times pi times the radius, right? 2 pi r. That fundamental formula is telling us something incredible. It means there are exactly 2 times pi arcs of length r around the entire perimeter of the circle. And since 1 arc of length r creates 1 radian, there must be exactly 2 pi radians in a full circle. 2 pi radians perfectly equals 360 degrees. That is the golden key. And this table right here, this is your time management matrix. This brilliantly illustrates the essential conversions you absolutely must commit to memory before you ever set foot in that exam hall. Everything hinges on the foundational fact we just proved. 360 degrees is 2 pi radians, which means 180 degrees is exactly equal to pi radians. From that single anchor point, everything scales down perfectly. Half of 180 is 90 degrees, so that's pi over 2 radians. A third of 180 is 60 degrees, so that's pi over 3. 45 degrees is pi over 4, and 30 degrees is pi over 6. Now think about our student Alex. Alex might memorize this entire table, but spend 5 minutes second-guessing it in the exam. Sam won't memorize it at all, and will try to manually calculate the conversion every single time, wasting precious minutes. You need to be better. Whenever you see an angle expressed as a fraction of pi in a Cambridge paper, your brain should instantly recognize it as radians. If you ever desperately need to convert a weird angle from degrees to radians, your strategy is simple. Just multiply by pi over 180. But these standard fractions, they need to become second nature to save you those critical minutes. Now let's move to Section 3. I'm going to show you exactly how this paradigm shift makes your actual exam mathematics so much simpler and faster. This is the transformation. I want you to look at the stark contrast on your screen right now. Imagine we are looking at an examiner's grading rubric. On the left side, we have the old, clunky degree formulas. To find an arc length or sector area using degrees, you are forced to figure out the fraction of the circle you're dealing with, meaning you write theta divided by 360, and then you have to multiply that massive fraction by the whole circumference or the whole area. It's a lot of writing, it's messy, it's highly prone to calculator errors, and it's exactly the kind of trap that student Sam falls into when rushing. But look at the right side. This is your mathematics success blueprint. Because a radian is fundamentally perfectly linked to the radius itself, the formulas become incredibly sleek. Arc length? It's simply the radius multiplied by the angle in radians. That's literally it. S equals r theta. Area of a sector? It drops down to just 1/2 times r squared times theta. When you use radians, the pi and the 360 naturally cancel each other out during the mathematical derivation. You are left with clean, elegant formulas that are vastly faster to use under intense exam pressure. Your mark potential goes from 0 to 100% just by switching your mathematical framework.
But here is the critical warning. These sleek formulas only work if your angle, theta, is in radians. If you plug 60 degrees into r theta, you will get a spectacularly wrong answer. Before we jump into our interactive workshop and apply these, stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, with our formulas firmly locked in, it's time for Act 4. Get your pens out. Let's build your exam strategy by applying everything we've learned to actual rigorous Cambridge Additional Mathematics past papers. We are going into the interactive workshop.
Okay, let's look at this data scan challenge from the November 2012 paper. I want you to mentally put 60 seconds on the clock and just look at the required steps. Cambridge exams rarely ask you to just plug numbers into a single simple formula. They layer concepts to test your analytical skills. Here, the command word is calculate. You are presented with a larger isosceles triangle that has an embedded circular sector inside it, and you're asked to find the shaded area in between the two shapes. If Sam were doing this, Sam would panic, try to find a single formula for a weird curved triangle, and fail. If Alex were doing this, Alex would calculate the perimeter of everything, which the question didn't ask for. Your strategy is logical, multi-step execution. Step 1, compute the area of the entire embedded sector using our sleek new formula. Area equals 1/2 r squared theta. The radius is 10, the angle is 1.5 radians. Boom, fast calculation. Step 2, calculate the area of the larger isosceles triangle using your standard trig area formula, 1/2 AB sine C. Step 3, subtract the smaller sector area from the larger triangle's area to isolate that shaded region. It's a test of recognizing overlapping shapes, decoding the command word calculate, and systematically executing the steps without panicking.
Now let's step up the difficulty. Find the flaw and how you might naturally approach this June 2014 paper 12 question. Look at that third bullet point. Show angle theta equals 1.696 radians. Show that is arguably the most dangerous command word in Cambridge mathematics. If you just grab your calculator, get 1.696, write it down, and move on, you will get 0 marks for that section. The examiner already gave you the answer. They don't care that you know the answer is 1.696. They are testing your framework. They are testing if you can provide the evidence and the explanation. You are given a circle with a radius of 8 centimeters and a chord length of 12 centimeters, but the central angle is hidden from you. You must methodically construct your argument. You have a triangle formed by 2 radii of 8 centimeters and a chord of 12 centimeters. You need to use trigonometry, specifically setting up the cosine rule, to prove mathematically that the angle is exactly 1.696 radians to 3 decimal places. You write out the cosine rule formula, you substitute the values 8, 8, and 12, you show the intermediate algebraic step, and then you state the final angle. That is the perfect mathematical Peel paragraph. Only after you successfully secure those marks can you speed write the rest, using your sleek r theta formula to find the arc length for the perimeter and your 1/2 r squared theta formula to tackle the area of the shaded segment. This question perfectly illustrates how circular measure isn't isolated. It is deeply, beautifully intertwined with advanced trigonometry. Which brings us to our final scenario, a massive challenge from the November 2014 paper. I'm going to present this to you, and I want you to figure out the system. You have a sector with an unknown radius labeled x and a known angle of 0.8 radians. Snug inside that sector is a right-angled triangle. The examiner hands you one vital golden piece of evidence. The area of that right-angled triangle is exactly 1/5 of the area of the entire encompassing sector. The command is to prove the radius x is 8.837. How do you frame this? Think about the 3 rules that guarantee top marks: command word decoding, framework application, and time management. You don't guess. You build an algebraic equation. You write the expression for the area of the triangle on one side. You write the expression for the area of the sector on the other. You multiply the sector's area by 1/5, and you set them perfectly equal to each other. From there, it's just algebra to solve for x. You have all the sleek radian formulas you need. Now, it's entirely up to you to apply them flawlessly. Listen, students who implement these exact mathematics strategies, decoding command words, framing their working, and mastering radians, see an average improvement of 2 full grade boundaries. But that only happens if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing right now. Our team responds to every single comment. Like and share this video with a study partner who needs to stop acting like Alex or Sam. Ace the exams. Your Cambridge success starts here. I'll see you in the next one.